The second part of the 6.4 Day 2 video lesson has us performing a different type of transformation on the sine and cosine function. The period of a function is defined as one complete cycle, kind of like one loop around our unit circle. That's why when we create the parent function for both sine and cosine, our table for x goes from 0 to 2 pi. In an equation, you know there's going to be a shift or change in the period for the function if there's a number that's multiplied to x after the sine or cosine term. What this number will do will change the period of the function from 0 to 2 pi to 2 pi divided by b. And this can give you a number with pi in it, but it can also cancel pi out and just give you an integer to work with. When we describe the transformation for the b value, it's going to look a little different. If b is greater than 1, we don't do amplitude for it, but if b is greater than 1, the graph actually compresses horizontally. So when a was greater than 1, it stretched, but now it compresses. Anything with x always does the opposite of what we kind of think it would do. And if b is a fraction or a number between 0 and 1, the graph will actually stretch horizontally. We have to make sure that we're looking at the number that's right by x, not the number that's out in front of the entire function. If we have that change in the period of the function, we need new input values. So now we're going to change our x coordinates. What you'll do first is set bx, whatever that number is with x, equal to 0. And then you'll set bx equal to 2 pi. Once you do that, just get x by itself both times. And that will tell you the new start location and the new end location for our table. Also, one more thing to note, if b has a pi in it, then we have to approximate on the x-axis. So if b has pi in it, pi will cancel out for our input values. Watch this table. It's going to be pretty aggressive. So I just drew a really big line because you're going to need this entire space. I'm starting at 0 because usually when you set bx equal to 0, you're going to get 0 for your first number, which is kind of nice. But then if you translate right or left and we have to approximate, pi over 2, we approximated that when we worked with a unit circle in the first part of chapter 6. Instead of writing pi over 2, we're going to write 1.6. And that's what you get if you just take pi divided by 2 on your calculator. Pi is approximately 3.1. 3 pi over 2 is approximately 4.7. And one loop around the circle, 2 pi would be 6.28, or approximately 6.3. But you know that on our graph, we kept going with the patterns last week. So we need to kind of continue this approximation so that we can get our points to fit when pi cancels out. The next value you'd want to go to is approximately 7.9, and then 9.4, and then 11, 12.6, well, I'm going to run out of room. Oh boy, 14.1. Hang on, I'm just going to slide this over for a second. And we'll get the last one to fit on here. Our graph goes all the way to 16, so our last number that we'll plot on this side is 15.7. You'll want to refer back to this as you describe the pattern, or as you kind of sketch the graph. We don't have to list all of these out, but this will help us when we sketch our graph once we've done those first 5 ordered pairs. Because guess what else? We also have to go in the other direction. Yikes. So over on this side, I know, I'm sorry you guys. To go to the left, negative pi over 2 is negative 1.6. Negative pi is negative 3.1. Negative 3 pi over 2 is negative 4.7. And then we'll probably won't go any further than negative 6.3 on the left. So thankfully, we don't have to go too much further on that left-hand side. Now, this is only necessary if b times x has a pi in it already. Otherwise, we don't have to worry about this one at all. All right, let's go ahead and see what this looks like on a sine or cosine function. Our first equation, y equals cosine 1/2 x. Notice technically in front of the cosine, there's no value. What that means is a equals 1. And if a is 1, I'm just going to change that a little bit for us here. If a is 1, then there's no change vertically for the graph. So there's no vertical change. It doesn't stretch or compress vertically. But the b value is 1/2. So b equals 1/2. 1/2 is between 0 and 1, so that would mean that the graph is going to stretch horizontally. It's going to look kind of like wider from left to right than the parent function does. And when we have that stretch, what we're going to do is just put a big star right here. To get our new kind of start point, we always set bx, whatever that is, equal to 0. This is really easy. If b is 1/2, we're just going to set 1/2 x equal to 0. To get x by itself, we would just multiply both sides by 2/1, multiplied by the reciprocal. And the 2's cancel out, which means x is by itself. On the right, 0 times anything is 0. So there's our new start point. More specifically, we're going to want to focus on where the new end point is for our table. To get that, we set bx equal to 2 pi. That's where the parent function ended. Well, now if we do 1/2 x and set that equal to 2 pi, and we multiply by the reciprocal, technically 2 pi would be over 1 as well. The 2's on the left cancel, giving us x, but watch this. If we take 2 pi times 2 on the right, that means our graph is going to stretch all the way over to 4 pi. So the curve is going to get twice as wide, but it's still going to stay the same height. So we're going to use these two pieces of information in our new table. But first, let's go back to our parent function rule. This is cosine, so you're going to want to sketch the cosine wave. And this is where we just create our table. We have x and y, so this is just the plain cosine function. We always graph our parent function first, just so that we can see the transformation. We have 0, pi over 2, pi, 3 pi over 2, and 2 pi. So that didn't change at all. And remember, cosine starts at 1. So 1, 0, -1, 0, and 1. All right, take a moment, everybody, pause your video, and plot those 5 points and continue the path edge to edge. When you play the video, that graph will already be on my picture, and I'm going to go right into the transformation. All right, here's what your cosine wave should look like when you're done. You'll notice on my graph, I doubled up the y values, so every 2 values was 1 unit, and we should be able to get everything to fit nicely on our graph. Now for the transformation. Here's what's going to make this look a little different. This will be the first time that we actually change the x values. So I hope that you're listening carefully here. It's not too difficult to do this, but it can get a little tricky sometimes. So let's see how this gets kind of tricky. We're going to start with 0. That's going to be the first number we put on our table. And then I'm going to draw my kind of like 1, 2, 3, 4, because I need to figure out those divisions, 2, 3, and 4. And I'm going to end at 4 pi. So that's going to go at the very edge. Now remember, these graphs are very symmetrical, so we want to figure out what's in the middle of these values. So I'm going to start in the middle of 0 to 4 pi. Halfway between 0 and 4 pi is 2 pi. So that's going to be that stretched version from regular pi up above. And then I'm going to go to this point right here. Halfway between 0 and 2 pi is 1 pi. And then let's see if we can figure this one out here. Halfway between 2 pi and 4 pi would be 3 pi. So you'll notice we're really stretching out these values. We're not going to any of the fractional kind of locations for pi on the graph. And then the nice thing about this one is we're just changing our inputs. Notice there wasn't an a value, so our outputs are going to stay the same as they were in the original parent function. So let's sketch these points and see what happens. 0, 1. And then I have to go all the way over to pi to get to 0. 2 pi is -1. And then 3 pi back to 0. 4 pi, +1. Can you see how stretched out that really is? And then to continue this pattern, we'd have to go all the way to 5 pi to put us back at 0. Now in the other direction, -pi, if we want to continue our pattern, would put us at 0. -2 pi would be down at -1. All right, so now to make this graph happen, if we start at 0, 1 and just kind of extend that curve, you'll notice it just kind of takes its nice, happy little time right here. comes up, back down again, and then in the other direction it kind of makes its way down and then goes back up. So can you see the stretch horizontally for this function? And there's your first horizontal transformation. Our next example has a vertical and a horizontal transformation. So this should be fun. Notice the number out in front of the trig term is 2. That's what A equals. And if A is 2, we always describe the amplitude. Start off just by taking the absolute value, which I know just equals plain 2 again. But if 2 is greater than 1, for the amplitude, that means this stretches vertically. And anything related to amplitude affects our y value. So we're not going to worry about this for the period of the function. This is going to change our outputs. So notice the parentheses pi over 2x. That pi over 2, oh, this is going to be fun. Pi over 2 is the b value. So right away, I want you to notice that if it's pi on the, or if b has pi in it, automatically that means we have to approximate our table. And if you look at the graph that I gave you, it's not pi over 2 and pi anymore, it's 1, 2, 3, 4, 5. So anytime b has pi in it, we're automatically going to approximate the table. So pi over 2, we know, is about 1.6. That's what we wrote on the front, or up above for the approximations. 1.6 is greater than 1, so that means the graph is going to compress, whoopsie, S, there we go, compress horizontally. So this graph is going to change in a couple of different ways. All right, so to determine our new start and our new end, remember we set bx equal to 0. In this case, it's pi over 2. And for now anyway, it's really going to be easy for our start. Our start will always stay at 0. The pi's cancel out and the 2's cancel out. But 0 times anything stays 0. So that's going to be where we start. When we add and subtract things onto this, we'll change this up. But for now, we'll keep it at 0. It's the end part that's going to be a little trickier to determine. So if we set bx equal to 2 pi, and b is pi over 2, to get x by itself, we're going to multiply by 2 over pi. But be careful on this right-hand side. Watch this, everybody. If I have 2 pi times 2 divided by pi, technically 2 pi is over 1. The pi's cancel, which is fine, but the 2's do not. So 2 times 2 would be 4. And that's where the full loop for sine will end, from 0 to 4. All right, so that being said, when we make our table for our parent function, we're going to have to go back up and use those first 5 approximate values at the top of the page. And it'll look something like this. We're just going to start with the plain sine wave. Okay, so we start with 0, that's fine. But instead of pi over 2, we're just going to go to 1.6 on the graph. So we're going to have to kind of approximate this when we sketch these values. Then 3.1, then 4.7, and then approximately 6.3. So you'll notice each time it's about 1.5 or 1.6 kind of from the last number to get to the next number. So we'll kind of approximate it that way. And then for sine, our outputs are 0, 1, 0, -1, and 0. So see if you can create this pattern just like we did up above. Pause the video and plot those first 5 points, and then kind of continue the pattern. And if you want to look at those approximated values after 6.3, you're welcome to do so. All right, at a quick glance, here's where I plotted my values for the approximation for the sine wave. So you can tell there's a little bit of symmetry to it. It looks like there's a couple spots where I could have maybe redrawn my curve a little bit better, but you just want to try to get as close to these values as possible. And then we look at the transformation. To create our table for y equals 2 times sine, and then of pi over 2x, to get our new inputs, we're going to start, remember, at that first value, and we're going to end at the second value. And I hope that you find this doesn't seem too difficult to translate. If we start at 0, and we have to do 1, 2, 3, 4 again. I'm just going to go 1, 2, 3, 4, and we end at 4. The halfway point right in the middle would be 2, and then halfway between 0 and 2 is 1, and halfway between 2 and 4 is 3. So you'll notice this is really going to kind of compress the graph. Every unit that we graph, we're going to have an ordered pair value. Now, don't forget we had that A value that's going to affect our outputs. The A value is 2, so that means we're going to take all of our original Y values and double them. So we started at 0, 2 times 0, 0. But our next Y value is 1, and that's going to double back to 0. Negative 1 is going to double to negative 2, and then 0 stays 0. Watch this set of values. 0, 0, and then 1 up 2, back to 0. At 3, we're down to negative 2, and 4, back to 0. That's definitely compressed from the parent function. So it compresses horizontally, but it's also stretched vertically from the parent function. So it's doing all the things we said it was going to do. To continue the pattern, at 5, I'm just going to go back up to 2, 6 down to 0, 7 to negative 2, and so on. Go ahead and repeat this pattern on the right-hand side. You can follow along with me or pause the video and do this on your own, although I do need to slide this over ever so slightly to the right. There we go. And we'll continue on. And we can go all the way to the edge to 16. Now in the other direction, if we go to negative 1 to continue the pattern, we'd have to drop down to negative 2. Back negative 2 at 0, negative 3 up 2, negative 4, 0, negative 5, down negative 2, negative 6, and then negative 7. So this is going to be quite the compressed sine wave. I'm going to pause the video to sketch this. I want you to sketch yours as well, and then press play and we'll see how we did. And here's what my transformation of the sine wave looks like. Hopefully yours is pretty close to this as well. We'll stop here for this video. Look on Schoology for further instructions.